Good morning, students. The topic for discussion today is about transformers. So far we have studied about DC machines, that is DC generator and DC motor. And I also told you that a machine like a DC motor or like especially a DC generator, it is not being used that much these days and its use is very limited. So now what we are going to study is about transformers. Is another type of a machine. Actually, it's not a machine what we say. It's like it's an electrical device. So transformer is an electrical device. It's a static device. It does not have any moving part. It's just a static device that transfer electrical energy from one electrical circuit to another through magnetic field without changing the frequency. So basically everybody might have heard like what is a transformer. Like you might know a transformer, it might have a primary, a secondary, and there is a small space between primary and secondary, right? So the primary side, which you call, actually that is an electrical side, and the secondary side is also an electrical side. So, and in between it is a magnetic medium. So transformer is actually, it's not a dynamic, there is no moving part. So transformer is a static device. So just basically, just I'm saying what is transformer, and the later detailed figure and all is coming in the next sessions and all. So now you just understand that transformer, they are all electrical devices. It is a static device. Why it is called a static device? Because it is not having any moving part like a generator or motor, which they have the armature and all. Here transformer, there is no moving part. So that's why it's called a static device, and it transfers electrical energy from one electric circuit to another through magnetic field. So through magnetic field. So primary and secondary. So it's an electrical, so electrical, magnetic, then electrical, and without changing the frequency. You know that frequency used in India is 50 hertz, or we can say time period which is 1 by frequency. Listen carefully, whatever I'm saying. So frequency is 50 hertz. So what will be the time period? 1 by 50, which is 20 millisecond. Yes, simple. Okay. So this figure shows a rough diagram of a transmission line which has a transformer. You know that power will be generated at the generating station. So it will 11 kV will be generated, and while it is while it is distributed to the other parts, it is made to pass through a transformer. Why? Because we want to step up the voltage. 11 kV voltage is stepped up using a transformer. So what is the function of a transformer? A transformer's main function is to step up or step down the voltages. So in a transmission, this is actually a pure electrical engineering. For just to give my students knowledge, I am saying like this is power system only. Like see my mouse arrow here, the primary side. So this we call the primary side. That is, primary side is the side to which we connect the source. So this is the source from we get the voltage. It's a generator, AC generator. So from here, so this is the primary side because it is connected. Source is connected to the primary side. So here we have 11 kV voltage, and this transformer is stepping up the voltage to 420 kV. So you understood what is the function of a main function of a transformer. So it is stepping up the voltage. So what is the advantage? A low voltage is stepped up and then only it is transferred. Why? Because when we step up the voltage, the current becomes proportionally reduced. How much we step up the voltage, that much current will be reduced proportionally. Because you know that the equation, current will be the MVA value. This is actually the MVA value divided by root 3 into 11, like just the equation only. So you understood that in the primary side, the voltage was 11 kV. So denominator, it will be 11 kV. So we will get an increased value of current. So I want you people to do this calculations. What is the current in the primary side and the secondary side? So in the primary side, you will get a higher value, and the secondary side, you will get a lower value, because in the secondary side, the voltage is a stepped up to value of voltage, so current will be less. So here we can see that the current value is very high. This result in high value of cross section. And so why we are stepping up the voltage and transmitting? Because when we step up the voltage, the current will be less. So if current will be less, means we need only a small conductors. Big cross section conductors we don't need, right? So small conductor means cost is also less. Just to give you an understanding of what is happening, what is what, that I'm giving this information. We will be moving on to the subject. So if the voltage increases, then the current value can be decreased. That's the point here. Okay. So we use transformers in many parts. Like here we are using, this is a distribution part. So here we are using transformers. Then in the consumer side, we use the transformers which we have near our house. That is the distribution transformer, right? So that transformer also we have, because every house, one locality, there will be one transformer, and from that transformer, the power is fed to our the distribution board in our home, right? So that transformer is also there. So basically, you must know that a transformer. So now I think everybody might have got an idea what a transformer, where we keep the transformer, why we keep the transformer, right? Yes, exactly. Now we are going to the use of a transformer, which include step up and down of the voltage level, as I told you now. Then it isolate the DC while it permit the AC. So one important function of a transformer is like only an AC voltage can be transformed, like stepped up or stepped down in a transformer. Got it? Yes. Because DC means that there is no change in frequency, there is nothing. So we cannot transfer a DC voltage, because if we give DC voltage to a transformer, it will get destroyed. Only AC, important. Then it is used for impedance matching. So this is actually related to networks only. You don't give more importance to this. Still, for maximum power to transfer from source to load, there is one, we go with some maximum power transfer theorem. So here we do the impedance matching. Primary and secondary, we do the impedance matching. That's it. Leave it. It's not important for you. Now, the three categories of transformers are normally divided into power transformers, distribution transformers, and instrument transformers. Okay. Then, while we are studying transformers, there are some important relations that you must know. When you study transformers, there are some important relations. Actually, you need not go much into the derivations of these relationships, because most of these derivations come from material science. So you need not study material science, right? So just understand, because about permeability and all these things, these are all material science concepts. So don't go much into the derivation, but still I will give you the logic why. So permeability is denoted by mu. I think this mu you might have studied earlier also in your lower classes. So permeability mu is given by mu naught into mu r, where mu naught is the permeability of free space and mu r is relative permeability. So permeability means how much. So you know that the transformer means there will be an inductor. Inductor will be there. The primary winding will be there. Secondary winding will be there. So a permeability shows how much magnetic field can pass through, right? Because there will be magnetic. Because I told you, like the primary side, then there is a magnetic medium, and then only we have the secondary side, right? So this phenomenon happens in the middle, which is the magnetic part. So that part should have it should be more permeable. Then mu r will be higher, than magnetic lines of force will be more. So mu naught is given by 4 pi into 10 raised to minus 7 Henry per meter, and mu r is the relative permeability. If mu r is high, then more magnetic lines of force we get. That's it. So just remember this equation. Now we are coming to magnetomotive force. So just like EMF means electromotive force. So we have EMF in electrical concept, and in the magnetic, like I told, in the middle part it is magnetic area. So here what we talk about is a MMF, which is magnetomotive force. So we can write that magnetomotive force is like this. Actually, just like EMF, electromotive force is responsible for current. Here, magnetomotive force is responsible for flux. So, MMF is equal to N into I, where N is the number of turns, I is the current through the turns. See, just see. So, this is the transformer, and this is the primary, and this is the winding, primary winding. And here we shows the N is the number of turns. So, in this figure, I have shown 3 number of turns. Okay. So, we can write MMF, the magnetomotive force induced, is equal to N into I, which we can also write as H into L. H is magnetic field intensity. How much intense the magnetic field it is, that is denoted by H, and L is the mean core length. So, for a transformer, this part we call as the core, and this is the winding. This one is the winding, and see, this is the winding, and this is the core, and L is the total length of the core, mean core length. Okay. So H into L can give you magnetomotive force, as well as N into I, the number of turns in the current through the turns. This current through the turns also can also give you magnetomotive force. Okay. Now we have the flux density, which is equal to, B is equal to 5 by A, that is Weber per meter square. This you might have studied in your lower classes also. In the 12th standard also, I think in physics you are studying, or in your basic electrical engineering classes you might have studied. Flux density is equal to flux per area, that is unit of flux is Weber and area is meter square, so Weber per meter square, and that can also be written as mu into H, and H magnetic field intensity. So substituting we get B into A is equal to mu into H into A, that is phi is equal to mu into H is Ni by L into A. So phi is equal to Ni by L by mu A. Just resubstituting this mu into A, we made it by mu A, so L by mu A it became. So normally we can write flux is, so the flux is the EMF, that is EMF here is MMF only. So flux is equal to MMF by reluctance, just like we say current is equal to voltage by resistance. Same concept here. That's it. So just like the current trying to flow through a low resistance path, flux will always try to flow through a low reluctance path. That's it. Okay. Now we are moving on to the right hand curl rule. So right hand curl rule is used to find the direction of magnetic lines of force, provided we have the direction of current, or the direction of the current if you know the magnetic lines of force. That's it. So we know that a current carrying conductor, so if we have a conductor and current is passing through it, a current carrying conductor, it always produces magnetic field, right? So whenever we have current carrying conductor, if the thumb shows current, then the direction of the coil shows magnetic line of force, right? Just remember. So you should hold your right hand. This is right hand curl rule. So just keep the right hand, the thumb open and other fingers curled. Then if the thumb shows the direction of, so here we can see that from right to left. So the direction of the current is from right to left. So the thumb will be from right to left. Then the curl, how the finger is curled, that shows the direction of magnetic field. So we can see the curl is the finger is your hand is being curled to the top part. So that means the magnetic field is going into. In your DC machine class, you already learned like cross means into and dot means the magnetic lines of force is coming outside, right? So that is the case. So we call this the RH curl. So if the thumb shows current, then the curl shows the magnetic field. And in other case, so this was a straight conductor. So here we will say we will go for a transformer and its primary side. Just understand this is the primary side of a transformer, and this is the way how the transformer is being winded. So we are given that this is the north pole and this is the south pole, and this is the way how the conductor is being winded. So we have learned already in your lower classes that in a permanent magnet, the magnetic lines of force will move from north pole to south pole outside, and inside from here, from north pole to south pole, it will be moving, and inside it will be moving from south pole to north pole. So here, in the north pole, the magnetic lines of force, here the flux is getting released. So we will apply the RH curl rule. It is also called screw rule also. Maxwell's corkscrew rule also it is called. So if we hold this conductor wrapped in our hand such that the thumb is flowing to the north, then the curling will show the direction of the current. So imagine holding this in your hand and this north pole shows your thumb, then the curling will show, that is from left to right, the curling will show you the direction of the current. Okay, so up to now what we have learned is the basic ideas, that is basic knowledge, whichever branch you have. Even a mechanical engineering student should, or even a other branch student, a non-electrical branch student, he should understand what and why we are using a transformer and when we use a transformer. Not just understanding the theory, not just understanding the peripheral things. Okay, so up to now what we have learned, like what is a transformer, we see application, why we step up, why we step down, we saw, then some basic equations we saw, then what is magnetomotive force, and how flux is produced, the equation, the equivalence equation, that is, MMF produces flux, EMF means electromotive force that produces current. So this is the basic thing. Now one important law that you should understand while deriving the an important, like if you are asked the principle of operation of a transformer, this is the main thing that you should write. So a principle of operation means there should be a primary winding, there should be a secondary winding. So you understood that there will be a magnetic core will be there, then there will be the winding will be there on primary side as well as secondary side. I will show you the figure, don't worry. 1 minute, because I captured the figure. Oh, this is 3 winding, you don't need that. I'll show you. Yeah, see, this is a transformer. Here it is the primary winding, and similarly here you will have the secondary winding, and this is what we call the core. So what we say is that whenever there is a voltage applied to the primary, an EMF will be induced in the secondary. Sorry, an EMF will be induced in the primary. Yeah, this is the diagram. So whenever there is a voltage applied to the primary, an EMF will be induced in the primary winding, that is N1. Don't see this figure over the direction and all, just understand. So an EMF will be induced. So similarly, this is a self-inductance. Self-induced EMF will be produced in the primary. Similarly, a mutually induced EMF will be produced in the secondary. So that is the basic. So how we can say that there is an induced EMF? That is being explained by using Faraday's law of electromagnetic induction, very important. So, Faraday's law of electromagnetic induction states that an EMF is induced across the coil if the magnetic flux linking a coil changes with respect to time, and it is given by E is equal to minus N into d phi by dt. So, plus or minus N into d phi by dt is actually that's actually the correct way of explaining, because E is equal to minus N into d phi by dt is like because in accordance with Lenz's law only, because Lenz's law opposes the change in flux. So only to denote that it opposes, we give minus. But a correct way of teaching a student is like Lenz's law means E is equal to plus or minus N into d phi by dt. But when you're doing problems and all, it is better to use minus N into d phi by dt. But this minus is minus actually don't have anything to do with the magnitude or the polarity. This just shows that the induced EMF opposes the change in flux. Only to denote that we are giving this minus here. So it states that EMF is induced across the coil. So it's a magnetic flux linking the coil changes. That is d phi by dt. What is d by dt means? Derivative means the flux is changing with respect to time. So E is equal to minus N into d phi by dt. Right? So that is what we called electromagnetic induction. Faraday's law of electromagnetic induction. So you might have heard one law which I mentioned in between, Lenz's law. So Lenz's law is also important in case of a transformer's principle of operation. So Lenz's law states that the polarity of the induced EMF. So you know that. So I already told you that whenever there is change in flux with respect to time, an EMF will be produced in accordance with the number of turns. So the polarity of the induced EMF should be such that it allows to cause a current. Then the current so produced must oppose the cause. So what is the cause here? Change in flux. d phi by dt is the cause here, which is the change in flux. I think this, apart from engineering, you might have studied it in your 12th standard also. Lenz's law, Faraday's law of electromagnetic induction. Then in the basic electrical engineering also, you might have studied this. That is E is equal to minus N into d phi by dt, and the polarity of the induced EMF should be such that it allows to cause a current that then the current so produced must oppose the cause. That's it. So here we have a magnet here. That permanent magnet is moved from position 1 to position 2. So flux is being reduced from 5 milliweber to 2 milliweber, and N is the number of turns. So don't worry about the direction of the current and all. I shall explain that to you later. So here E is equal to, as per the Lenz's law equation, E is equal to plus or minus N into d phi by dt. So all these things we have, the number of turns is 2000 and flux change is 5 from 5 to 2. So we get the answer as 60 volts. So we can say that the current flows in a direction to oppose the cause of induced EMF. So what is the cause of induced EMF? The movement of the magnet from position 1 to position 2. So by moving, because of the movement of that magnet only, we get what we call change in flux. Okay. So these things are actually not important for you people. Just for my knowledge only, in your exam, you need not write these things. Okay, so this is actually the case of a three winding, because we have transformers with three winding also. So those who are interested in understanding more about the transformers, you can refer back, because in your syllabus you need only two winding transformers. So three winding transformers also there just for your best purpose, because one day if somebody is asking you whether we have a how many windings, is there a chance to have a third winding for a transformer? You should say yes. Yes. So the reason why I am teaching you all people from scratch to like the higher turn topics, because even after 10 to 20 years, no, even right now you might be in your 20s. So even after 10, 20 years, if somebody is asking you, like maybe your son is asking you, Papa, what is a transformer? What is being done? So you must be in a position to tell to him like, oh, this happens there. There is a magnetical area in between. So there is flux will be there, flux change will be there. And you should say Faraday's law of electromagnetic induction. So, like, it's a matter of pride, when you're able to say all these things even after 20 years. So, understand and learn whatever you have in your syllabus. That's very important. Whatever you're learning, now understand practical applications, you should understand, and then you should try to understand the concepts, and then you should go for your previous year questions, and then you should work it out. Like from the scratch, you should go for the higher thoughts, and then you should write the exam. Okay. Yes. So that's all for you in today's class. So we shall see the what about an ideal transformer and its working. So far in this class, the main thing you should understand is the principle of operation of a transformer. So all these things, according to the how much mark it is asked, you can make it compact and write. So transformer story should come just like the movie Transformer. You know the story. This story also should come to you like in a flow. Okay. Thank you.